Hi, everyone. Welcome to our 54th session of the MedAI Group Exchange. This week, we have Tri Dao from Stanford University here with us to present his work on FlashAttention, fast and memory-efficient exact attention with I/O awareness. Tri is a PhD student in computer science at Stanford, co-advised by Chris Ray and Stefano Olmo. He works at the intersection of machine learning and systems. His research interests include sequence models with long-range memory, as well as structured matrices for complex deep learning models. His work has received the ICML 2022 Outstanding Paper Runner-up. Thank you, Tri, for joining us today. Before we start, could you let us know how you want to take questions?
Yeah. Thank you, C. So I'm really excited to be here. So this is a fairly informal talk. I'm so happy to take questions during the talk. That's great. And yeah, thanks, C and Nadita too for organizing this. I'm really excited to be here.
Okay, so let's try to make this session as interactive as possible. Without further ado, let me hand it over to Tri.
Yeah, thanks. Yeah, so I'm really excited to be here talking about our recent work. It's called FlashAttention, and we try to put all the main ideas in the title. So what this is going to do is attention, we're going to make it 1, faster, 2, is going to be more memory efficient, and 3 is going to be exact. So we don't do any approximation. And the trick is called I/O awareness, and I'll go into a little bit of details. So that all the high-level takeaway messages are in the title. All right, so let me talk a little bit more about the high level. So what we're going to do is we're going to use I/O aware tiling techniques to speed up attention. And attention is the heart of transformers, which is now the dominant machine learning architectures in many fields. Okay, so what does I/O aware mean? I/O just means in and out, reads and writes. So the thing we're going to exploit is that on the left, I'm showing a diagram of GPU memory in SRAM, and by exploiting SRAM, which is way faster but way smaller than GPU memory or HBM, we're going to make things go faster. And the trick for doing that, as I've shown in the middle, is you're going to compute things by block, and that's called tiling. And the upshot is on the right, we're going to make it faster. We're going to save a lot of memory, and we're going to have higher quality models. So those are the main takeaways. So before I dive into the details, so I want to talk a little bit about motivation and why this could be relevant to folks working in medical medical domain or medical AI. So our motivating idea is we want to model longer sequences, and Chris, my advisor, and a bunch of us put out a blog post as I linked in the bottom here about why we care about long sequences. And there are three main reasons. One is we want to bridge new capabilities. So the anchoring application is in natural language processing, where we want to model books and plays and instruction manuals, not just paragraphs. And the second reason is we want to close the reality gap. And the anchoring application here is computer vision, where we've seen that if you can model images at higher resolution, you get better and more robust insight. And high resolution generally translates to longer sequences. And the third one, which is probably the most exciting, is we're going to open up new areas. So things like time series, audio, medical imaging, video, things like that. They're naturally modeled as sequence of up to millions of steps. So that's why we care about long sequences. But the problem is that the dominant architecture, machine learning architecture nowadays, the transformers, they have trouble scaling to long sequences. And I'll go into why. But the problem we want to tackle is that we want to scale transformers to long sequences. So that's the high level motivation. And I'll go into 3 examples in some medical applications, why you should care about transformers and why you should care about transformer on long sequences. The first, this is in collaboration with Armin at the the psychology department. So we're interested in building, for example, foundation models for brain decoding from fMRI readings. So surprisingly, you can use the same transformer model that's been used in natural language processing to build, representations for brain decoding. And Armin has a great paper on this. And we want to make this faster. We want to make this more memory efficient so that we can model, let's say, longer time scale when you do fMRI decoding. So that's one thing we're excited about. This is ongoing collaboration with Armin. The second application, motivating application, is with Arjun, who's a PhD student in W and in medical school, where we want to model high resolution MRI images. So these are knee MRIs. And usually two of the tasks you care about is detection and segmentation. And as you see, for radiologists, they usually care about these tiny regions that if you can't model along or high resolution, the models will tend to miss these regions. So the goal again is to model high resolution images, and that translates for transformers to long sequences. And the third application, this is in collaboration with Gautam, is on megapixel and gigapixel histopathology, which is a very similar application that, for example, the talk last week from Richard, he also talked about gigapixel histopathology. So let's say the task here, you might want to predict tumor versus healthy tissue at different image levels, or you want to do object detection for tumor lesion. And for pathology images, these are usually stored at different resolutions, and you want to model and incorporate information from different resolution, be it at the cell level, or be it at the organelles level, and things like that. So you need to be able to deal with really high resolution images, and transformer nowadays, they can't quite do this yet. There's a bunch of tricks people have to do. But again, we hope to make transformer able to model long sequences so that they can deal with these high resolution images in these applications. So those are the three motivating applications, why we care about transformers for long sequences. So that's kind of the motivation. And then, so the talk will have 4 parts. I'll talk about some background, then I'll talk about our proposal, FlashAttention. And then I'll go into empirical validation, and finally a little bit on future directions. And feel free to ask questions throughout the talk. I'll also pause periodically for questions. So before we go into the background, happy, I can pause here and see if people have questions. All right, so let's get into the background of why transformers have trouble modeling long sequences. So just many of you might be aware of the transformer architecture already. This is just so that we're on the same page in terms of notation. So transformer is a machine learning architecture where you stack a bunch of these blocks for encoder or decoder, the 2 types. And each block consists of 2 layers, the attention layer and the MLP layer. And we'll focus on the attention layer because that's usually the bottleneck for long sequences. And attention, it looks like this. Many of you might have seen this. So this is just so that we're on the same page in terms of notation. The inputs, you would have the query Q, the key K, and the value V. And the steps are that you would take Q and K and you multiply them together. Optionally, you apply some masking. Then you do a softmax to normalize things, and you apply a dropout optionally. And then you multiply that with V to get an output O. And the thing that prevents attention from scaling to long sequences is that naively, attention has compute and memory quadratic in sequence length. Here, sequence length I denote with N. And the reason it's simple is because you have to deal with these big N by N matrices. So you need to, N square amount of memory to store it. You need N square amount of compute to process it. So that's the simple answer. And you can think of M as, let's say, 1,000 or 2,000. And then D, the head dimension is usually around 64 or 128. So n by n really is where the quadratic blowup happens. So we want to address this. So we want to understand what are the bottlenecks. And the bottleneck turns out to not be computation. The bottleneck is in memory reads and writes. So what do I mean by that is there are a bunch of intermediate steps where you have to deal with this n by n, deal with matrices of size n by n. And so that means a lot of times it's just going to be spent on just reading and writing into memory. And that really slows you down, as I'll show you with some profile. And so naively, it requires a lot of reads and writes from slow GPU memory. HBM, it's just the technology, what you think of as GPU memory. And there's a paper from MLSys last year that we really like, called Data Movement is All You Need, where they study transformers, and they found out that, yeah, the bottleneck is data movement, which is just reading and writing data. It's actually not computation, and that's quite wasteful. So we're very much inspired by that paper. And just as a preview for the result, so here I'm comparing against the PyTorch attention implementation and our FlashAttention implementation, and they compute the same thing. We're not changing the output. We're not changing the math. They compute the same thing. But turns out PyTorch, when you compute attention, most of the time is spent on these memory-intensive operations, masking, softmax, and dropout, whereas the matrix multiplication, counterintuitively, they don't take that much time. Even though matrix multiplication takes the most floating point operations, it's the memory reads and writes that really hurt you. And so FlashAttention is a way to compute the same thing, but with significantly reduced memory reads and writes. And we can go, in this case, maybe 6 times faster. So to understand how we do that, we need to understand a little bit about how GPUs work. So this is a very brief background on GPU. And here I'm showing some diagram. Let's say your machine has a bunch of GPUs. And each GPU you can think of as having a pool of memory. Which, if you type NVIDIA SMI, it shows you 32 gigs. That's the HBM. That's the amount of GPU memory you have. But when you do computation, what happens is that the data is loaded, the input is loaded from the HBM. It gets loaded to the compute unit and the SRAM, which is, you can think of as analogous to CPU cache. It gets loaded from HBM to the compute unit. All the computation happens there, and then the output gets written back to HBM. So it turns out this loading and writing of data to HBM actually is the bottleneck. And I'm linking here at the bottom a blog post from Horace, who's a PyTorch developer. Is an excellent blog post on understanding what are the bottlenecks for a lot of these deep learning operations. So it's a great blog post, and I highly recommend it. So, okay, so how do we, so we see that there is an asymmetry between the HBM and the SRAM. So HBM is usually quite fast and it's quite large, but SRAM is even an order of magnitude faster, but it's, let's say, 3 orders of magnitude smaller. This is what I'm showing on the right. And these numbers are for the A100 GPUs, but other GPUs are similar. So the question is, can we exploit this asymmetry in the memory hierarchy so that we can get speed up? And the answer is yes, with IO awareness. That means we want to account for different, account for reads and writes to different levels of memory. So we're going to try and reduce the reads and writes to GPU HBM. So that's the main objective. We're going to reduce reads and writes. So that's it for the background. I'll pause here for questions, either about attention or about GPU architecture.
So sorry, Trey, I just have one quick question since nobody has it. Like,
Yeah.
So when you do the metric multiplication operation, are you saving it as a different variables, or you are saving just overwriting the same variables? It seems that you are just overwriting, right?
Yes. So here we're dealing with the an n-by-n matrix. So yeah, you can, I guess, save memory if you just write to the same location. Yes.
Okay. Okay.
Yeah. In practice, when you train models, people don't do that because generally, when you do training, you need to store the intermediate value so that you can compute gradient in the backward pass. So in practice, most of the times people don't write to the same location. But yeah, it's a great idea. You can write to the same location, maybe save, I don't know, 4x memory or something. Yeah.
Right, because I would imagine like in the PyTorch, exactly the PyTorch operation that you were showing for the attention, I think they are also not really, or not only like time efficient, but they are not also like memory efficient. I don't know if you have any solution since you are just doing the multiplication. It's kind of like inverse functions. I don't know if you thought about like optimizing also the memory at the same time of optimizing the time.
Yeah, so that's a great point. So as we show that you can be clever and not materialize these n-by-n matrices at all. So in the end, you get something like 10x memory savings overall. So one thing about reading and writing to the same location is that you still need to, in terms of memory, yeah, you do save the total amount of memory, but in terms of time, you still need to do the same number of reads and writes.
Right.
So you might not get speed up, but you might save some memory. Yeah, I agree.
Okay.
Yeah.
Could you explain why the dropout and softmax actually takes much more time than the?
Yeah. So this is a little bit surprising. So turns out most of the time is actually spent on reading and writing to memory. So every time, let's say you start with A, you take Q times K, you get the matrix A, and then you apply some masking. And what really happens is actually you're not doing any math. What you do is load the value from HBM to the compute unit. The compute unit sets some of the values to 0 or negative infinity, and then it writes back down the output. So it has very minimal floating point operations, but the amount of memory reads and writes is much larger than matrix, or at least double the matrix amount of memory read and write when you do matrix multiplication. So this is a little bit surprising because attention, most of the time you think things are bottlenecked by computes. If you reduce the amount of computation, you would go faster. But for attention, it's a little bit counterintuitive. Is that the time is taken by memory reads and writes? Matrix multiplication turns out to be faster than these masking or dropout or softmax operations.
I see. Thanks.
I had a quick question, but for dropout, if you're doing random dropout, you won't need to like load anything from HBM, right?
So you still do need to load things from HBM in the sense that because for each GPU operations, it's called kernel, the input starts out in HBM. You need to load it into HBM. You set some of those to be 0 and you write it down to HBM. So that's generally how the architecture works.
I see. So if we prevent that from going down to HBM before doing the dropout, then that can save time. But I guess we still need to do it for the gradients. So
yes, so that's an excellent idea. Actually, people have tried it. Attention is so well studied that people try all ways to all the ways they could think of to optimize these things. And they can combine like, hey, let's just load, let's say combine softmax and dropout. You can load things in, do softmax, and then just apply dropout before you write the output out. So it is an excellent idea, and people have done that, and they have seen some speed up. But again, generally, you need to materialize at least one of these n-by-n matrices, and that's still quite a bit slower. Yeah.
Got it.
But
thanks.
Yeah. So there are more optimized implementation here. We're comparing against PyTorch, but the excellent people at NVIDIA, they have a bunch of different implementations, and we do compare against them to combine some of these steps to reduce I/O. So from a hardware perspective, it's very much known that you want to redo reads and writes, and you can combine some of these operations. But so far, people haven't been able to combine all of them. And as we'll show, there's a little bit of subtlety, but you can do it, and you can get the whole thing much faster. Yeah, great questions. All right, so I'll go into details of how we actually do this. And the one trick is actually really simple. So before that, as I explained, we want to reduce the memory reads and writes to HBM. And the answer usually is that you want to compute things by blocks so that it's small enough that it fits into SRAM, that you can load from HBM to SRAM and just do local computation on SRAM. And so you don't need to repeatedly read and write to HBM. But there are two challenges. One is that the softmax as defined, it needs the whole row before you can do softmax by definition. That's challenge number one. So if we want to do things by block, it's not clear how you would do softmax if you want access to one block instead of the whole row. And challenge number two is that when you train models, you usually need these intermediate values so that you can, in the backward pass, you can compute gradients. So if we want to save memory or if you want to reduce reads and writes, if we don't save these large attention matrices, how do we compute the backward pass? And we use two well-established techniques to address these. One is called tiling, which just means tiling just means doing things by block. But you need to restructure the attention algorithm a little bit to get to get things to load from HBM to SRAM and the compute attention kind of locally. It needs a little bit of a trick to get the right answer. And the second technique we use is called recomputation. So the answer is we don't store the attention matrix from the forward pass, we recompute it in the backward pass. And it turns out recomputation is actually faster than storing it and reading it again. So that's a little bit surprising. And I'll go into details of some of these techniques. So the way we implement it is that we have a fused CUDA kernel so that we have fine-grained control of the memory reads and writes, so we can control where to place what. And we provide a PyTorch interface that people can use. So let's go into details of some of these techniques. The first one is tiling, and this is, you just need a little bit of math. This is the only math in the talk. The trick is that you have a softmax over, let's say, a large attention matrix, but you can break it up. Let's say you can break it up into two pieces. So if you want to compute softmax of A1 concatenated with A2, you can actually compute softmax of A1 first, then compute softmax of A2, and then you can rescale them using these scalars alpha and beta. And you can work out exactly what alpha and beta are. The details are in the paper, but they're pretty easy to work out. So softmax, you can actually break it into smaller softmaxes so that you can exploit locality. And when you apply to attention, you're going to have softmax of A1 and A2 times the V, the value matrix, V1 and V2. And you can decompose it exactly the same way. So you get softmax of A1 times V1. So that's a local computation. Another local computation is you take softmax of A2 times V2, and by rescaling things and adding things together, you get the right answer. So mathematically is the same answer. You're just doing the computation in, let's say, a different order. And the nice thing is that you can exploit locality, because here we don't need to load the whole of A1, A2 in. We just need to load A1 and V1, and then we compute whatever local things we need. So this is the only trick that you need to know. And the algorithm is relatively simple. So we're going to load inputs in block by block from HBM to SRAM. So on the diagram on the right, you can, HBM is in green and SRAM is in orange. So you can think of conceptually, we're computing attention block by block, and for each block, we're going to load whatever inputs we need from HBM to SRAM. We do whatever local computation, and then we're going to write down the output to HBM. So we never materialize this big n by n matrix. And with that, you get memory saving and you get speed up, as I'll show you in some of the benchmarks. So tiling, that's the idea. You analytically rewrite softmax a little bit so that you can do local computation block by block. So that's the main idea.
I had a quick question. So in this case, the alphas and betas are not constants, right? They depend on A1 and A2.
Yes.
Yes.
Yes, that's right. So when you load in A1 and A2, you also need to compute, let's say, as one scalar per row. So it's dependent on the data. You're right. Yeah.
So then you can't do it by the block because alpha depends on A1, A2, and beta also depends on A1 and A2, right?
So alpha only depends on A1. Sorry. Yeah, no, you're right. So alpha depends on both A1 and A2, but it depends on just one scalar. They're just normalizing scalars from each block. So you can think of it as, you have a summary statistics of each block, and then based on the summary statistics, which are really small, you can combine them. Yes.
I see. So you first so you compute the summary statistics, and okay, yeah, that makes sense. That can be easily done when you are computing the A1 and A2, right? So
yeah. Yeah, great question. Okay, so that's the first technique, tiling. This technique's been known in a while. Tiling in general computing block by block is kind of the cornerstone of databases, graphics, numerical linear algebra. And this trick of decomposing softmax, the first time we saw it was in 2018. So these are well-established techniques that we're using. But surprisingly, these simple techniques will allow us to go faster and more memory efficient. Okay, so that's the first technique, tiling. The second technique is recomputation, and conceptually is also very simple. So you don't store the attention matrix from the forward pass. In the backward pass, you recompute it. And if you already have these normalization factors, alpha and beta, you can actually recompute it pretty quickly, since the inputs you need are going to be loaded from SRAM anyway. So in some sense, computation is almost free because you're already doing the reads and write to load inputs in. And again, we don't store this big N by N matrix. Everything is loaded in and then compute on SRAM. So the memory requirement is much smaller. We incur much fewer reads and writes, but we do incur more flops. And here I'm comparing the standard implementation with FlashAttention and this table. And first of all, in terms of flops, we actually incur more flops. It's about 12% more flops because we recompute things in the backward pass. But in terms of HBM reads and writes, so memory reads and writes, we're about 9 times smaller. And in terms of runtime, we're about, in this case, like 6 times smaller. So even though we recompute things, even though we incur more flops, surprisingly, it actually speeds things up. Again, the observation is that attention is not bottlenecked by computation. It's bottlenecked by reads and writes. So you want to reduce reads and write, even if you have to incur more computation. So that's the second technique. And so those are the two techniques that we use. These are well established, but surprisingly, attention's been out for 5 years. Is one of the most studied problem in machine learning. But surprisingly, no one has done this. So it's pretty cool. You can put together these simple techniques with a little bit of a twist, and then you can make attention go faster and more memory efficient, even compared to the best, the strongest baseline we compare against, which I'll go into. Yeah, so I'll pause here for questions.
Like another question I had was, how do you make sure that this affinity from the block to the SRAM is maintained in like the PyTorch implementation for your FlashAttention?
Yeah. So that's the difficult part. So we had to implement this in CUDA so that we can decide, we can control when to load what things. So that actually took significant time. There's like 2 grad students writing CUDA for 3 months or something. But we're excited about a couple of things. One is that we're collaborating with compiler researchers so that we can automate a bunch of these things, so that compilers can do it for you. Number 2, some people, some other researchers really like this, so they independently re-implement it in JAX or in Triton. Triton is a Python-like high-level language, so it's not as painful to write. So we're excited about that. Hopefully, this will be accessible to researchers. If you just want to use it, then we have a PyTorch interface. You just call it, and it's going to run. If you want to tinker with it, then some of these higher level implementations in higher level languages could be pretty useful.
Awesome. Yeah, that's great. Thanks.
Yeah. Okay, so those are the techniques we use to speed up attention. Again, the goal is so that we can allow transformer to model long sequences. And now we're gonna I'll show you some empirical validations on how this helps us with that goal. So we're gonna benchmark the attention module. We're gonna show that it is faster, even when you put it in end-to-end model. So you get faster end-to-end model training of transformers. And again, we're not changing the model at all. We're computing the same thing, just faster. And the second thing is that we're going to save a lot of memory. So it allows to model longer sequences, and that leads to higher quality transformers. So first, when we benchmark just the attention module, we see that in terms of speed, is about 2 to 4x speed up compared to the standard implementation from PyTorch or Hugging Face or whatever people commonly use. So this is, we have a chart on A100 where we get 2 to 4x speed up, depending on whether you have masking or dropout. And in the paper, we have more comparisons with approximate attention and sparse attention and so on. We also benchmark on a bunch of different GPUs. I'm not showing here. All the charts are on our GitHub repo. Yeah, generally you can we observe about 2 to 4x speed up of attention. And again, attention is a very well studied problem, and surprisingly, you can get substantial speed up, even though tons of engineering effort has been poured into improving attention implementation. So that's just attention module, you get 2 to 4x speed up. And when you measure memory usage, which is the total memory you need, the nice thing about FlashAttention is memory is linear in sequence length. It's not quadratic. So depending on sequence length, we can see either 10x or 20x memory savings for the attention layer alone. So this allows to scale up to 64 sequence length of 64K on one A100 GPU. And just for context, some of the largest transformer models have context length of like 2K, just because of this quadratic blowup. So if you have memory linear in sequence length, you can scale to much longer sequences. All right, so now we're going to plug FlashAttention into a model, and we're going to train end-to-end, and we'll see that it leads to faster end-to-end training. So the first one we want to compare is BERT-large. It's an extremely commonly used model. And the benchmark the benchmark we're going to use is MLPerf, which is a highly optimized standard benchmark for training speed. So this is a comparison where all the models starts from the same checkpoint. They train on the exact same data, same validation data, and you just measure how long it takes to reach a certain accuracy. So everything else is the same. The model is the same, just the different implementations, different algorithms, how fast do they run? And if you use a commonly used Hugging Face BERT, then this takes like 55 minutes. If you use the MLPerf implementation from NVIDIA, which was the world record when we submitted the paper, this is extremely optimized. Teams of engineers have worked on this, so they're like 2.5x faster than Hugging Face. But surprisingly, FlashAttention can be even faster than the previous MLPerf record by 15%. So it is really exciting for us. So we're also 2.2x faster than Hugging Face BERT. So if you're training BERT and you're using Hugging Face implementation, you're leaving around 2x performance on the table. So the second model we can compare to is GPT-2, and we're training GPT-2 small and medium from scratch on this commonly used data set called Open Web Text. And again, we compare against Hugging Face, which is very commonly used, and we compare against the strongest baseline we could find, which is Megatron LM. Again, an implementation from NVIDIA that's been used to train some of the largest language models. And we see that we get the same quality. We in terms of training time, we're about 3 or 3.5x faster than Hugging Face. So again, if you're using Hugging Face, you're leaving about 3x on the table. And the models are the same. We're not changing the model. We're only changing the algorithm and the implementation. So the upshot is you get faster training for a bunch of these transformer-based models. I'll pause here for questions.
So do you start analyzing also the attention visualization for this model just to see like if there is any difference in the attention output? Or I know that it is more or less like mathematically it's exactly the same, but I don't know if you have analyzed like how the attention output looks like in the normal model versus your FlashAttention.
Yeah, so we haven't visualized things. We did some spot check where the outputs are the same, or up to numerical precision, like 1e minus 4 or something. So the outputs are the same. Yeah. So I don't expect the attention pattern to change. If you want to change the attention pattern, then there's some other methods where you say, oh, I want to add this to the attention so that it's biased towards like local features or global features or something. So we haven't explored that. Yeah, but that could be interesting.
Okay. So you didn't have any kind of like linear operation performs on the attention and just to see like if there is any change in attention. So you just analyze it's more like a training speed wise, right?
Yeah, training speed wise. The training curve look identical, so they look like they lie on top of each other. Again, it's because we're not changing the model.
Right.
Yeah.
Okay.
All right, so here we can change the model and we can train transformers on longer sequences, and that generally leads to higher quality. So here's an example, again, GPT-2, but we increase the context length. And usually when you increase the context length, it goes slower. But generally it gives you a better model, and this is measured by perplexity, where lower is better. And surprisingly, when we increase the context length by 4K, we're still faster than Megatron LM at 1K, and we achieve lower perplexity. So this is really exciting, and in fact, a few companies are looking to use FlashAttention to train language models with longer context up to 8K. So this stuff actually works. So one longer context, it leads to better language models. The second one, let's say, is a classification model. This is a classification task where you have a bunch of long documents. These are either physician notes, that's mimic, and then the second one is a legal reasoning task. And the sequences could be pretty long, up to 10K. And when we take a pre-trained model and we extend its context and we fine tune on this classification task, we see that we immediately get some improvement in quality by just simply using longer context. So yeah, this makes sense. And so one synthetic task that's pretty cool is called PathX. This is more of a benchmark task to see if transformer, how much you can push transformer into the sequence length. And the task looks like this image where there are 2 dots and a bunch of lines, and you're supposed to say whether the 2 dots are connected. And in this case, it is not connected. It's a classification task. So it's more of a benchmark synthetic task. You're not supposed to use patches, so you actually need to process 1 pixel at a time. Your sequence length is either 16K or 64K. And in the past, people have tried, and basically no transformer can get better than chance performance, either because they run out of memory, they're too slow to train, or they do some approximation and it can't pick up these signals at all. And so what's really exciting is FlashAttention used the first transformer that can solve these tasks better than chance. So it can go up to sequence length 64K or 16K or 64K. So that's something we're pretty excited about. I'll pause here for questions before going to future directions.
What's the difference between flash attention and block-sparse flash attention here?
Yeah, so I didn't mention this. Turns out flash attention, you can also impose sparsity, which is, so far I've talked about only doing exact attention. We're not approximating anything. For there's been a long line of work on attention approximation, and one such way to do it is impose some sparsity. So if you similarly impose some sparsity, flash attention is again compatible with that, and that allows you to reduce the computation by exploiting sparsity at the cost of some approximation. So for the largest task path 256, where the sequence length is 64K, flash attention would run, but it would take like a month to train. But block sparse, if you impose some sparsity, it finishes training in like 3 days or something. It's one way you can push the sequence length even longer by using some approximation. But for the most part, flash attention, that it just does exact attention, is not approximating anything. Yeah.
I see.
All right, so let's go into some future directions that we're pretty excited about. The first is just getting it into more people's hand. So the PyTorch developers are integrating this into PyTorch torch.nn transformer. The Hugging Face folks are integrating into their models as well. And independently, other researchers, they were excited about these ideas, so they re-implemented it in JAX. The OpenAI folks re-implemented in Triton, which is this Python-like language that's a little bit higher level than CUDA. So that's a little bit more friendly for tinkering. And the second one, there's some technical work. You see that the ideas are actually simple. So maybe compilers can support, automatically do these things. And so far, right now, they are not able to because they need a little bit of math rewrite. But we're collaborating with compiler researchers so that some of these techniques could be done automatically. And maybe in the future, your model will just get faster, more memory efficient automatically. And the third one is a high level point, which is we want to bring hardware-aware thinking into other deep learning operations beyond just attention. And we believe this is a big and important idea. And in fact, it came from things like databases, where for decades people have been trying to reduce the I/O, and it's been hugely successful. So the more AI question is, what can we do with longer sequences? We're really happy that several companies are looking to use flash attention to train language models with 8K context length, which is about 4 times longer than the largest models right now, GPT-3. GPT-3 can have context length of about 2K. So people are excited about pushing this further to get better models. Another thing, as I mentioned in the beginning, is we want to model highest resolution images, be it from MRI images or pathology images. Maybe high res images will give us better insights or better models. So those are the things we're excited about. So in summary, flash attention, it is fast, it is memory efficient, and it is exact. So it doesn't do any approximation to attention. And the two key ideas are tiling and recomputation. And the upshot is you get faster model training, or you get better models with longer sequences. And with that, I'd like to conclude. So thanks so much for your attention. And our code is open source. If you go Flash Attention or you go to our GitHub, we have links to everything. And yeah, we're excited to see how modeling long sequences with Flash Attention, what kind of new capabilities it's going to give us. Yeah, thanks for your attention.
All right, thanks, Chi, for the amazing talk. Let's all give him a round of virtual applause. And is there any questions from the audience?
Yeah, happy to take questions as well. Yeah.
When you mentioned high-res images, what sort of matrix are you thinking, or like bit depth too?
So one application we're collaborating with Gautam is these pathology images, where they're either megapixel or gigapixel. So that's like I think the largest one they have is 50K by 50K with 100 channels, and that's generally just way too big to do anything with. And right now, people just cut them into patches and process one patch at a time. So maybe we can do something there. Let me see if I can find these. For MRI, I think the resolutions are like 512 to 512, something like that.
Yeah, that's about right. Even 256 there sometimes.
Yeah. So again, that's still larger than what people, current models can support.
I'm wondering what's the longest sequence length you have experimented with using FlashAttention? Yeah,
so the longest we've tried is either 16K or 64K. And I think that corresponds to images of like 256 if you do it by pixel. If you do patching like VIT, then that could correspond to high resolution images. Yeah. So sequence length is about 16K to 64K, which again is quite a bit longer than most common transformers.
Yeah, makes sense. I guess for the histopathology images, it can be tens of thousands patches, or even more than that. So
yes,
I can see that FlashAttention could be a very good, could be very useful here.
Yeah, I guess like if you can do 64K, then you can probably you just like take the square root of 64K and those many patches. It's still a huge context length for pathology images for sure, and probably can work on whole MRI images completely then, right?
Yeah, hopefully we'll get there. This is an active research, and if you're interested, please talk to us. This is an area we're really excited about. So we'd love to talk to you.
Is there any other question? Okay, if not,
thanks so much.
Let's thank Tree again for the talk, and thank you everyone for joining us today. We will upload the recording of this talk to our YouTube channel later today. And if you have further questions, feel free to reach out to us or to Tree directly. Thank you, everyone.
Thank you, Trey. Thanks for giving the talk. Bye.
Yeah.
See you.
Bye.